Hello friends, good afternoon and welcome to EduSet Live Lectures. Dear friends, as you know that we started a series on organic chemistry and today we are conducting yet another lecture in the same series. In today's lecture, we will be talking about the concept of conformation. To discuss this topic, we have with us our subject expert Dr. Pankaj Khanna. Dr. Khanna is Assistant Professor in Department of Chemistry in Acharya Narendra Dev College, University of Delhi. Without further ado, I would like to welcome Sir to our studios and request him to start the lecture. Welcome, sir.
Thank you so much, ma'am. Hello, viewers. So we have done in a series of lectures earlier under the topic of stereochemistry, and we have discussed all the concepts related to optical isomerism and geometrical isomerism and CIP rules, RS configuration. There is one more topic in that series that is called as conformations. So we would be talking about that in detail in relation to the cyclic compounds as well as acyclic compounds. So starting with conformations, the first thing is the preview of the lecture. We would be talking about isomers. So we would be in a few seconds we would be talking about what are isomers. Then under the topic of isomers, what are conformers. Then we would be in detail talking about torsional strain, the type of things which are present and give rise to different conformations. They are torsional strain in terms to ethane, then steric strain in terms to butane, then angle strain for the cyclic compounds, and then a little bit about the substituted cyclohexanes. So starting with the lecture, what are isomers? Isomers are different molecular structures with similar molecular formula. So when molecular formula is same and the structure is different, they are called as isomers. And we have done all the types of isomers present in this diagram, except the constitutional isomerism, which comes with the structure relating to positional and the changes in the functional group, or other type of like the change of the type of functional group. These are the type of constitutional isomerism. And in stereoisomerism, it is the isomerism in space. The arrangement of atom differs. Out of that, we have done the configurational isomerism already, which covers the part, as I have already said, geometrical isomers and optical isomers. So those which are related to plane polarized light, and geometrical ones like the double bond, the cis and trans and all. So the leftover part is the conformational isomers. So this term conformation comes from the fact that we are changing the structure of the molecule by virtue of the rotation of single bond, carbon-carbon single bond. So we would be dealing with this in today's lecture. So what are conformational isomers? They are, or sometimes they are called as conformers. What are they? They are nothing but the different structures which are obtained by the rotation of CC sigma bond or CC single bond, carbon-carbon single bond. So this rotation, as we would be doing in a few minutes, gives rise to different structures. So sometimes when I am going through this topic in my class, a few times I say that actually they are not isomers, because if I stand up or I sit down, I am the same person. So I am not a different person altogether. So isomers are two different compounds. So if I am in a different state, if I am consider myself as a molecule and I am in a different state or a different direction, raising my hand or putting something like that, so I would not change my identity. So they may be confused as whether they should be called as isomers or not. But recently when I was teaching this concept in the class, I found that because of the rotation around carbon-carbon sigma bond, there are other type of isomerism also, like we have already seen in the previous slide about the optical rotation, optical isomerism and other isomers. So they may be generated because of the fact that you are rotating carbon-carbon bonds. Actually what you are doing are conformations, but they give rise to different isomers. Also when this different type of isomerism is not there, or simple cases, molecules have been isolated in a frozen state, or we can say under freeze conditions in a matrix, low temperature matrix, at different positions or different structures. So they are called as conformational isomers. So we would be talking about these conformational isomers throughout the lecture, and there are infinite, because carbon-carbon single bond, when we rotate it, then there may be infinite number of possible structures. So, out of those possible structures, we would be mainly talking about the important ones, like out of the thousands and infinite number of the structures, we would be focusing on the primarily those structures which are either towards the higher side of the energy or towards the lower side of the energy. So, we would not be talking about the intermediary structures. So, let us start with the molecule of ethane, because we have a carbon-carbon single bond only in ethane. There is no carbon-carbon single bond in methane. So, we cannot have conformations in methane. So, what is happening? Let us see what happens in ethane. So, you can see on the slide that I have placed a structure or molecule of ethane in this, with carbon as black dots and the hydrogens as blue circles. So, the carbon-carbon bond is this one. This one is the carbon-carbon bond. It might be, the carbons may be visible as grey color also. So, this carbon, these two carbons are the two carbons of ethane. What are the hydrogens there? These Y, they are making the one hydrogen 2, 3. This is one CH3 group, and the other CH3 group is on the back side. So, these are the two CH3 groups attached by virtue of this carbon-carbon single bond. What I am doing now is I am showing you how I am not rotating the molecule through the carbon-carbon single bond, but I am moving the molecule so that I can show you one of the alignments of the two forms. So, I am moving the molecule. You can see on the slide that I would be moving the molecule on the slide. This carbon-carbon ethane, can we have the slide please? This carbon-carbon ethane molecule is, when it is moved from one point to another, the structures which appear on the slide are one behind the other. So, can we have the slide please? The carbon-carbon molecule structure is like this, and when I am moving this slide like this, so the carbon, one carbon is eclipsing the other carbon. The one carbon in front is eclipsing the behind carbon. So, they are exactly behind one another, and all the hydrogens present here are also behind one another. So, this hydrogen is masking the behind wala hydrogen, and this one, when you see from this side, is exactly in front of the this hydrogen atom. Same is the case here. So, this form is may be projected, what is called as a sawhorse projection formula, or sometimes it is, some authors write it as Andreon formula, by this structure. So, we are depicting the carbon-carbon bond by this line, and these Y are all the hydrogens. So, I have not intentionally I have not placed all the hydrogens here, because I am depicting one of this form. Similarly, when I convert it into other type of formula, you can see this is a Newman projection formula. So, if you place all the hydrogens here in three positions, this Y, all the hydrogens, then this Y is coming up front, the hydrogens are present here. What is this circle? This circle is the black portion of carbon. If I look from this side and this carbon is exactly in front of the behind carbon, the carbon at the rear, then the rear carbon is not visible. So, this circle depicts the front carbon, and the behind carbon is almost invisible. Also, these all front carbon hydrogens are all visible with complete bonds, but as you see, if you put the carbon up front, the behind hydrogen like this, in this case you can see that this hydrogen is partially, the bond is visible only in partial form, all the bond is not visible. So, when the carbon at the rear is not at all visible, because it is exactly behind the front carbon, and the front carbon also masks or eclipses the bonds of the carbon hydrogens in the rear carbon. So, this form is called as the eclipsed state. So this is the eclipsed form of ethane, where one carbon is present on the exactly in front of the other, with all the hydrogens also eclipsing the rear hydrogens. So if you can put your hands like this, then you can make it the structure, you can make it like this, that the two carbons are behind one another and the hydrogens are eclipsing the other hydrogens. So this is one form. Second form is the staggered form. What now I have done, I have rotated the first carbon, I have kept the same Y condition, and I have rotated the rear carbon in a inverted Y position. So what is happening, again I will move the molecule to in front of you, and this is the main form in which the carbon again comes up front the carbon, but now the hydrogens are not behind one another. So these three bigger hydrogens are of the front carbon, and the smaller hydrogens are of the rear carbon, thus making this type of a sawhorse projection formula, where the front one is a Y and the rear one is an inverted Y. So we are not having the eclipsing of hydrogens of the front carbon eclipsing the hydrogens of the behind carbon. So this is the case, and this form is called as the staggered form, because we can see that we may say that the form has all the hydrogens are staggered, they are not placed one behind the other. So these are the two forms of ethane. Now how would you make the differentiation in terms of the energy, because if I place the eclipsed ethane, the hydrogens are one behind the other. So if you can see me, the hydrogens are eclipsing in the case of eclipsed ethane. Ethane staggered situation will arise when I will rotate the bonds, and so when I will rotate the bond, the hydrogens are now in a staggered position, and this condition is much more stable than the eclipsed one. Why is this so? Why is this so? Because of the fact that the hydrogens in the eclipsed form are one behind the other. So you can see me now that I have placed two Y positions like this. So this is one Y, this is the front carbon with a Y, the two bonds are my thumb and my finger, and the arm is my third bond, carbon hydrogen bond. These are the three carbon hydrogen bonds, and the carbon carbon bond is this one, finger touching the other arm. So this bond, carbon carbon bond, I have placed in this manner. So if you can see in the camera, the front carbon hydrogen bonds are actually eclipsing these fingers, these behind carbons. So these are in the eclipsed state. When I rotate it like this, when I am rotating it like this, it is clockwise from, when you are watching on the channel, then it is a clockwise rotation of the back carbon. I am rotating it like this, so I have placed in between. So this is the staggered form. Now these two hydrogens, carbon hydrogen bonds, are not eclipsing. I cannot move my arm like this by virtue of the bond. These two hydrogens are not masking, but they are having in a state where this bond is not interfering that much as it was doing in this state. So when they are in the eclipsed form, what happens that the carbon hydrogen bonds are exactly one behind the other. When they are exactly one behind the other, the interelectronic repulsions of the carbon hydrogen bond makes it, or it converts it into the staggered form, which is the more stable form. So the eclipsed form is this one, then the staggered form, such that the distance between these carbon hydrogen bonds is increased from 0 degree to 60 degree. So we are moving from 0 degree to 60 degree to 120 degree, then 180 degree, and then so on and so forth. So in the case of ethane, it does not matter, but in the case of butane and others, it will matter, and we will come to that. So what is happening, this eclipse form is having, although a mere 3 kilocalorie per mole or 12 kilojoule per mole of energy difference with the staggered form, the below one, but it is still the less stable form than the staggered form, because of the fact that the carbon hydrogen bonds are repelling each other, and that causes what is called as the torsional strain. So the concept of torsional strain comes from ethane only, that the carbon hydrogen or maybe any other group, the bonds which are present in the front carbon and the back carbon, when they are exactly one behind the other, then they would repel because they are having electron pairs, and the repulsion would lead to or tend to form the staggered form, which is comparatively more stable than the eclipse form. So we would be doing this thing in the whole of the lecture, this torsional strain kind of thing, but we would be introducing more of the strains. So what is a strain? Strain is something like if I am putting a glass of water in my hand for half an hour, so it would start paining me. So I would tend to put it in a stable form on the table and release my hand. So I have to release myself from that strain. Similarly, ethane releases itself from strain in the eclipse form to a less strained form, which is the staggered form. So torsional strain may be compared to the recoiling of the wires, like we had the landlines we have. There is a recoiled wire which is of the handset, and when we put it straight, and when we release it, it again goes back to the same shape. Now you would ask me, why, if there was torsional strain and something like this, and there is eclipsed and staggered form, why the forms are changing? Why staggered may not remain as staggered? Why is there that these two conformations are arising in ethane? This is because of the fact that the energy difference is so low, 3 kilocalorie per mole or 12 kilojoule per mole is so low energy difference that it may be achieved by the collisions only. So molecules, ethane is a gas, and when you have put it in a bottle or in a balloon or in some container, the molecules will be in a state of collision. So when they collide, they exchange energy with one another, and they move from the stable staggered form to the unstable or less stable eclipse form. However, they cannot remain there for long because of the less stability, and they will convert back or release energy to go back to the staggered form. So these are the reasons why the conformations arose, and we are doing this topic. So this is all about. And what is torsional angle? The plot you can see on the slide. There is a plot which is giving you, the diagram is giving you the energy curve. It is plotted against energy and torsional angle. So torsional angle and energy are related here. And what is a torsional angle? Torsional angle, I told you, like I had the eclipse part, this is 0 degree. The hydrogens are carbon hydrogen bond of front carbon and the back carbon are exactly behind one another. So this is 0 degree. When I move my back wala carbon like this becomes 60 degree. So there is a 60 degree torsional angle now. I move it further, then I would move to 120, 180. But this does not matter in the case of ethane, because ultimately if I move it like this, so I have moved to say 120 degree. Now these two are also in my hand, they may be seen as different because one is a thumb and one is a finger, but in case of ethane these two are both carbon hydrogens. So they would not differ and they would not have any difference whatsoever. But for you I have prepared the structure in this manner. So you can see the slide that I have placed, although the hydrogens are same, but I have colored one hydrogen as blue and the other one as red, and I start rotating. I keep the front carbon Y as Y, and I start rotating the next carbon. This is the original one. The second one, I have rotated the red hydrogen clockwise with an angle of 60 degree. So this becomes, from eclipse it goes to staggered, and then I rotate it again by 60 degree, it becomes eclipse again, and then I rotate it again by 60 degree, it becomes staggered again. Then again this is say another 60 degree rotation. Then finally the last staggered one 300, and when I move to 360 degree, I have rotated completely 360 degree. 360 degree is as good as 0 degree, and I have reached the original form. So which was the front form. So these are the rotations for ethane. Now what happens when I move from ethane to propane, the curve remains the same, but I have placed on the front Y, I have placed in place of blue hydrogen, I have replaced it with a methyl group, because propane is your CH3, CH2, CH3. So this is the CH2, the front carbon I am placing here, this is the C2, the behind carbon is again CH3, this is it is the C3, and front CH3 is this. So what is happening? In this case, the plot remains the same. We have one eclipse, one staggered, torsional angle 0 degree to 60 degree to 120, 0 degree, 60 degree, 120, 180, it goes like that. The plot remains the same, the difference arises in the energy. So the energy barrier, which was in case of ethane, it was 3 kilocalorie per mole or 12 kilojoule per mole. Now it has come to 3.3 kilocalorie or 14 kilojoule per mole. So energy has increased. Why? The difference between the eclipse and the staggered form, the energy has increased because of the fact that earlier there were, both were carbon hydrogens. These two were hydrogen. ये भी hydrogen है, ये भी hydrogen. Both are carbon hydrogens. But in case of propane, the front one, this one is a methyl. When it is a methyl, then the behind wala is again hydrogen. So let us see on the slide what is happening. So when I move from ethane to propane, the energy difference between eclipsed and staggered is increased. What is happening? Ethane 3 kilojoule per kilocalorie per mole. It is now in propane it is 3.3 kilocalorie per mole. Torsional strain is present in both. So what I have talked about interelectronic repulsion between carbon hydrogen bonds, it remains the same. Now why is the difference in the energy? It is because of the steric strain. So I am introducing now the new concept, which is the steric strain. Why it is there? We will see that in case of ethane, the hydrogen was only repelling because of the bonds of carbon hydrogen, which was the torsional strain. But the hydrogen and hydrogen were quite apart. They were at a larger distance. When I replace the red hydrogen with methyl, so what is happening? The methyl group has a carbon in place of hydrogen, and then another hydrogen comes in this place. So the difference between hydrogen and hydrogen in ethane is now decreased when I have placed a methyl group in place of hydrogen. So now this hydrogen and this hydrogen are quite nearer than the hydrogens of ethane. So what will happen? When they are quite nearer, they will be having van der Waals repulsion, and that causes what is called as the steric strain, and that causes the 0.3 kilocalorie per mole or 2 kilojoule per mole of energy difference. So this difference arises because of the steric strain, which is because of the methyl and hydrogen. Now you would understand this concept to a greater extent in case of N-butane. So let us quickly go through what are the conformations of N-butane. So N-butane, you can see the slide, and starting with 0 degree. So I have replaced from the propane, in which I had replaced hydrogen with one methyl. Now I am replacing the other hydrogen also with a methyl. So there are two methyl groups present behind one another. So it is called as the fully eclipsed form or the 0 degree torsional angle form. I move the angle from 0 degree to, I move the red methyl clockwise, and I go to the 60 degree angle, torsional angle, and I have a very stable form, which is called as the staggered, we have called it, but we will have the different nomenclature in this case, we will come to that. The staggered form we have here, and then I will move further and get the 120 degree, which is again an eclipse form. Then I move further to 180 degree, and I found that there is another staggered form. So let us stop at this, and because the rest of the conformations are the same, what is happening when methyl and methyl were behind one another, exactly behind one another, they were having very much high steric strain. We would be coming to that, and it is the high steric strain because of which this is the highest or the most unstable form of butane. This is called as the fully eclipsed form. When we move to the staggered, in this staggered form, although that highest strain is released, but still there is some difference, some proximity of the methyl and methyl. So this is the staggered form, but not the most stable one. So this is called as the gauche form. Then we move again to 120 degree, the eclipsed form again forms, but this is not as strained as the fully eclipsed, because now the methyls are in a state of propane, methyl behind front and hydrogen behind, methyl behind and hydrogen in front. So this is the strain of propane, not of the fully eclipsed. So you can see that this is in lower energy than the fully eclipsed form. Finally, we go to the methyls in the staggered form. They are opposite to one another. So we call it as NT, and this is the most stable form. You may be asked in the exam about drawing the conformations of butane and giving the most stable and the least stable conformations. So the next three are the repetitive ones. This is again partially eclipsed, and the next one again the gauche staggered, and finally we reach to the maximum unstable fully eclipsed form. So what is happening in this case? Let us see the examples once again. This one is called as fully eclipsed because methyl is exactly behind methyl. In this case, it is partially eclipsed. Methyl is eclipsing, but the hydrogens. So there is less repulsion than the fully eclipsed. And in case of when we compare the staggered ones, these are the two new. The eclipse form has converted into two new forms of eclipse, fully eclipsed and partially eclipsed. As similar to the lunar eclipse or the solar eclipse, we say that in a solar eclipse it is a total solar eclipse. So the masking of or the eclipsing of the sun is complete, and the whole of the sun is masked behind by the moon in between. So moon is having in between, and the sun is completely masked. And there are other eclipses which are happening, which are partial eclipses. So this is the same concept. Then in case of staggered ones, you can see on the slide that I have converted the names of staggered into two forms. One which is gauche, there was some interaction, but in the other case which is called as NT, the methyls are way apart. So they are not close to one another, and so we develop two different forms of the butane. So you can see this, what I am telling you, the methyls in fully eclipsed. Now you can see the methyls are having these two hydrogens very close to one another, and because of this, fully eclipsed form is the least stable one. We change to gauche. The gauche one has the no torsional strain, and much more the hydrogens are, you can see with the size of the arrow, the hydrogens are quite far, but still they are in the staggered form, they should be free of any strain, but still they are having strain because of the fact the hydrogens are not as far as in the case of NT form. So finally you can see this slide in a moment that in the partially eclipsed form, the difference between the hydrogens is not that different. As if we can see the slide, the hydrogens are still eclipsing the hydrogens of methyl, but they are not behind one another. The difference is less than the case of partial eclipse. So thank you very much for your patience. Welcome viewers. We are talking about conformations in today's lecture. So before going to the cyclic compounds or the cyclohexanes or the cycloalkanes part, I would like to draw your attention to yet another case of the acyclic compound, which is a special case, needs to be mentioned here. As in the earlier part we have done the conformations of butane. So in this case I have taken ethylene diol or ethylene glycol, it is said. So the conformation in this case, we have done the conformation of butane and we found that the anti-conformation is the most stable one. Then the Gauss forms or the Gauss staggered are two forms, they are the lesser stable with maybe 0.9 kilocalorie per mole difference only, and then the partially eclipsed and the fully eclipsed is the least stable. So there are a few exceptions or anomalies. So one of the anomalies, as you can see on the slide, is ethylene glycol. So ethylene glycol, what is happening in this case is that the Gauss form of ethylene diol or ethylene glycol is having a hydrogen bond. As you can see on the slide, that the hydrogen bond formed in the ethylene glycol is stabilizing the Gauss form. So we have the staggered form because Y is up front and inverted Y is in behind carbon, but these OH should not be it should not be the form which should be most stable. I have written Gauss most stable, not the anti one, because of the fact that the hydrogen bond gives us that much energy or stabilization which was required to move from Gauss for making Gauss being the most stable one than the anti, because the difference between Gauss and anti was anyways 0.9 kilocalorie or say maybe 3 kilojoule per mole or 4 kilojoule per mole. So this was very less difference and this was covered by the hydrogen bond, and now in this particular case the Gauss becomes the most stable one. In other cases also, like the dichloroethanes, 1,2-dichloroethanes or 1,2-dibromoethanes, there is a concept of dipole-dipole interaction. When I replace the chlorines by the methyls of butane by chlorines, then the ratio of anti to the Gauss ones changes. Like in case of N-butane, it is 67% anti form, but in case of 1,2-dichlorobutane, it goes to 73, and when I go to bromines, then it goes to maybe 80 something. So why this is happening? This is happening because the size is increasing from methyl to chlorine, relatively similar size, but when we move from chlorine to bromine, the size of the atom is increasing, so steric hindrance is increasing in case of Gauss form. So the anti form becomes much more predominant further, and also in the Gauss form there is some dipole-dipole interaction which is happening because of the proximity of the halogens in the Gauss form which are nearer than in the case of anti form. So this was one concept which was which I thought that I should discuss with you. And now we move on to cycloalkanes. So cycloalkanes are, you must be knowing that cycloalkanes are counterparts of the alkanes with the closure of the ring. Like in case of propane, when we remove 1,1 hydrogen of propane and combine that CH2 with the other CH2, we will get this. These are not geometrical figures, but cyclopropane, cyclobutane, cyclopentane and cyclohexane. So what is happening in this case? This case I have brought here will introduce you what you call as ring strain. So we have talked about torsional strain, then we have talked about the bulk strain or steric strain. Now we will be talking about this ring strain. So what is happening? You can see that there was one scientist or who proposed a theory, as you have already seen on the slide, Baer strain theory. So he proposed that the bond angle in a tetrahedral is, we all know that 109 degree 28 minutes. So what I am doing when I am moving this ethane, say methane, I am placing one carbon here and one other carbon here. So it becomes a propane, CH3, CH2, CH3. Now if I close this ring by removing 2 hydrogens from each carbon and make a cyclopropane kind of system, the cyclopropane ring is now a triangle type of thing, and you can understand that a triangle has each angle, an equilateral triangle has 60-degree angle. So what I am doing, I am compressing this stuff of 109 degree to 60 degree. So this compression Bayer talked about and said that the molecule becomes again a new type of strain which is called as angle strain, and this strain is present in cyclopropane, and you can see on the slide that I have written all the bond angles in the ring structures. The bond angle in cyclopropane is 60 degree, in case of cyclobutane it is 90 degree, in case of cyclopentane it is 108 degree, and in case of cyclohexane it is 120 degree. So the deviation from tetrahedral angle of 109 degree, it is maximum in case of cyclopropane, then cyclobutanes, then cyclopentane was having nearly the same 109 and 108 degree. So it should be like 1 minute, it should not be 0 degree, it should be 1 minute 28 seconds, and then 10 degree 28 seconds. So what Bayer proposed was that the rings are when we are taking these angles, then the proposal was that the rings are planar. So we can have the angles as typical of the geometrical figures of triangle, rectangle and other polygons. Then he proposed that as the deviation increases from the original tetrahedral angle of 109.5 degree, then the angle strain increases and stability of the ring decreases. So he proposed that the cyclopentane should be the most stable one, as you can see on the slide, that it should be the most stable one because of the least deviation. And the second point he proposed was for the larger ring the strain increases with size. So what I have written on the slide is cyclopentane most stable, least deviation, and larger rings strain increases with size. So was it correct? No, I have painted it into red. So what I have done, I have painted the wrong statement into red. So this was wrong because of the fact that cyclopentane was not the most stable one out of the 4 present here. Was the second point correct? No. So the Beer-Stein theory failed in a procedural manner because of the fact that when the experimental values were taken and the delta H combustion per CH2, I have divided CH2 by N, the number of carbons per CH2 data was taken. It was found it was nearly 157 for acyclic molecules, the propanes, the butanes and the pentane hexane. For the cyclic compounds, the deviation was in conjunction to the Beer-Stein theory. For the cyclopropane, the deviation was maximum, then cyclobutane it was alright, it was a little lesser, but for cyclopentane it should have been, there should have been no difference, but that was not the case. There was certainly some difference coming up, and the one with the most stable structure which came around was that of cyclohexane without any ring strain or without any difference in the delta H combustion data as compared to the acyclic hexane. So it was found that Beer-Stein theory, although as of today is also used and it is taken into account, that is why I am dealing it within the lecture, but it had its own disadvantages, or we may say that there was a failure of the theory because cyclopentane was not found to be the most stable one, but the cyclohexane was the most stable form in the case of these 4 alkanes. So you can see on the slide that the 2 lines, the statements I have written in red change into the other statements, like it was given by Sachs and Moore theory that the structures are not planar. The difference was that the structures were not planar, and what happened, you can see on the slide that cyclopentane ring was not found to be more stable, but cyclohexane was the most stable form. As for the another statement, larger rings also do not have the strain, as I have written for given by Bayer, that strain increases with size, but this was not the case. What is the case? You can see on the slide that for the larger rings, the rings are strain free. So the changes are cyclopentane is not most stable, but cyclohexane is most stable, and larger rings are strain free. If we go to the level of C30 or even maybe C12, C13 rings, then there is no difference of energy by delta H combustion data with the cyclic structure and the acyclic or the long chain compounds. So this was found by Sachse and Mohr theory, that this is the case, that the rings are not planar but they are puckered. So we will come to know what are puckered rings, and because cyclohexane is the most stable, we would be dealing in the lecture with the cyclohexane only. So this is the structure of cyclohexane, which is the most stable form, and if you have read it earlier, then you would find that this is called as a chair form of cyclohexane. As we are sitting on the chair, then there is a back seat, then there is a front part, and there is a leg space going down. So this is the chair form. You can see on the slide that when I am now talking about the conformations of cyclohexane, because out of the all we can talk about cyclohexane because it is the most stable of the given 4 we have talked about. So what is happening in the chair form, we move from chair to a chair which is like this, looks like a chair on the beach side. On the beach there is a chair which is on which you can spread your legs, and so the bottom part of the chair comes up front and it goes up front to parallel to the ground, and it becomes a half chair form. So this is a half chair form. Then we come, this is a very high energy state, and it is not exactly a state but it is a transition state. So it cannot be said to be one of the conformations. We have only 3 types of conformations, we would be talking about those mainly, but it needed to be mentioned as half chair is a part of it. So when I further pull what I did was I pulled this leg part, this you can see the arrow in the chair, this leg up parallel to the ground. So I got the half chair form. Now again I twist it like this. When I move it in this manner, then the half chair form becomes a twist boat form, which is a lower energy form than the half chair. When I keep on twisting it like that, I have this cone as up front like this. So I reach to a form which is called as a boat form. So in this form, this dark part is the part which is coming towards us. So I have plugged it again up front, twisted it to the twist boat, then further twisted it to make it exactly same as this one. So this is a boat form. So why I am telling you all this? Because this is the conformation, this is a carbon-carbon single bond rotation which is happening in the cyclic form and giving rise to different type of structures. So these all are conformers of cyclohexane except that of half chair, which is a transition state. Now what I do, I started with pulling this leg part of the chair upwards and got the boat part. As in case of butane, I told you that when we reach NT, the second part is the replication of the previous one. So the upcoming conformations are nothing but the previous ones. Now I start pulling it down from this side, from the other side, which was the back of the chair. So this back side I twist it like this a little bit and get a twist boat again, and further when I twist it and put it to the parallel to the ground, I get what is called as a half chair again. And when I pull it down like this, I get my chair back. But this chair is the mirror image of the original chair. So what is happening? All the carbons are changing the conformations from this chair to this chair, and this is called as flipping of the cyclohexane. So, this is flipping, the back seat has now become the leg part and the leg part has now become the back seat. So, what is happening? These are the states, and what is the energy difference in between these? This chair to half chair is 43 kilojoule per mole, chair to twist boat is 23 kilojoule per mole, and from twist boat to boat it is 3.7 kilojoule per mole. So, with this slide we come to the fact that out of all of these, although half chair seems to be the most unstable form, but as I have called it as a transient state and it is not available to us or it is not visible to us, I discard it completely out of these all isomers. So, we are left with chair, twist boat and boat. Out of these three, the boat is the most unstable form and chair is the least stable, unstable. So, boat is the most unstable or least stable and chair is the most stable form. So, we would be describing these two, because as in the case of butane and ethane, we describe only the most stable and least stable. So, we would be describing why chair is the most stable form. For this, you have to visualize the fact that this is the chair, placed. You can place a chair in front of you and you mark these carbons as 1, 2, 3, 4, 5 and 6. You go behind the chair and look from this side and this side. So, now I am rushing into things, but we have to complete the part. You take it individually as 1 and 2 as the 2 carbons of butane. Forget about the whole of the cyclohexane and take it as 1 and 2 are the 2 parts of butane. So, what would happen when I draw this structure like this? The chair is, this is the top of the chair, the back side. This 1, 6 and 5 make the back side. So, I am standing behind the chair. Behind the chair I am standing and this 3 is going down. So, this 3 is the leg part or going downwards where our legs or the floor is there. So, this 6 is the topmost of the back side. So, what I would do, I would look from 1 and 2 and forget about all these 4 carbons, 6, 3, 4, 5, forget about these and look at 1 and 2 as a butane. So, when you look at it as a butane, you will see that the 1 and 2 are in staggered form. Why? Because 1 is having this hydrogen is coming out, this hydrogen is going there and this 6 carbon is coming out. So, I have placed first carbon is this one, 6 carbon and these 2 are hydrogens. So, I have not marked them. So, these 2 are hydrogens and this is the 6th carbon. So, they are coming like this, but the behind carbon what is happening? 2 is having the hydrogen going down. In 1 the top hydrogen was coming up and in 2 this carbon hydrogen is going down. So, this is coming up, 1 wala carbon having a hydrogen up and 2 going down. Similarly, the second carbon hydrogen is going up, but parallel to this the first carbon is going down and same the third carbon is going down from 2 and like this and the 6th carbon is going up like this. So, I can take it as 6 as a methyl and 3 as a methyl, then it will form a gauche conformation of butane. This was the first step of formation of Newman projection of chair form. Now, what we do, we take another look at 5 and 4. So, when I look at 5 and put 4 behind it, I can again have the similar butane kind of conformation with this Y like this and this is an inverted Y, this 3 and this one. So, this gives you the conformation like this. I have placed the 5th carbon, 4th carbon is behind this, the 6th carbon is going up, the 3rd carbon is going down and rest are all hydrogens as the previous case. So, what I have done, I have taken 1 and 2 as a butane and 4 and 5 looking from 5 side, for 5 and 4 as a butane. So, these 2 are butanes and when I make it the 3 and the 6 as the same, I get the chair form Newman projection formula. So, it is a little bit difficult for you to understand why 6 is going up, because seemingly 6 is going 6 is closer to me, so that is a bigger atom. But you can see that these two second and fourth carbons are also away from me, but the third carbon is still smaller in size because of the fact that it is going downwards, and this sixth carbon is bigger in size than 1 and 5 because it is coming more towards me, or it is on the higher above area. So, this is another Y form. This Y form is coming like this, and this Y form is coming like this. What I have done is I have combined the two butanes by 6 as common. I have mixed the two butanes, coupled them into one another and form this common 6 here. And similarly, the two methyls I have replaced with one CH2. So, I have combined the two butanes to give you the chair form of the cyclohexane. So, what is happening in this case? Y chair is more stable because of two reasons, that all carbon, this is not the case that I have made the conformations from 1 and 2 and 5 and 4. You can draw from any side, you can take any two carbon pairs, and when you draw a structure you would get a structure like this. You may also get a structure in which the front one is an inverted Y and this 6 wala carbon is going down, and the behind one wale carbons are having the proper Y structures, and this 3 is going up. So, that may be the change, or it may be a mirror image to this, but all carbon-carbon bonds are staggered. Why? Because of the fact that the cyclohexane is not planar as suggested by Bayer, but it is in a pucker state as suggested by Sackes-Moore theory, and the eclipsing is not present in that. It would have been present if the structures were planar. All the carbon hydrogen bonds would have been behind one another. So, there would have been much more destabilization because of the torsional strain also. But still there is a little interaction because of the gauche interaction of 1,6 and 2,3 carbon-carbon bonds, and this exists as in case of N-butane. The gauche form had 0.9 kilocalorie per mole, or maybe 3 to 4 kilojoule per mole of energy difference. So, this is the cyclohexane chair. Now, we move on to the lesser stable cyclohexane boat. So, I have drawn again the similar kind of boat structure which I have drawn in the plot, and again we would look at from 1 and 2. We looked at 1 and 2 in the earlier case, and from 5 and 4 again we would be looking in a similar manner. What is happening when we look at 1 and 2 and 5 and 4? Now, there are in the case of the earlier structure, I had drawn it with the help of balls and all the colored material, but in case of boat I could not do it because it is typically a very clustered structure. Because it is an unstable structure, it is much more clustered. So, when I look it from the one side, I get 1 here, 2 is in behind, 3 comes behind on top. So, this 3 is, when I am looking from this side, the 3 would be behind and 6 would be coming up. So, if I say that 3 is a methyl and 6 is a methyl, this is an eclipse form. Why in Newman projection formula there is a little difference? Because I cannot exactly mask one another. If I mask one another, then the hydrogens and the methyls would be behind one another, and we cannot depict the structure. So, we relatively a little space is left in between the front carbon bonds and the behind carbon bonds. So, this is happening here. Similarly, if you look from 5th carbon to the 4th carbon, 5th carbon is up front, 4th is behind. In this case, the 3 would be behind and coming towards the left side. 3 was coming towards when I was looking from this side from 1, 3 was coming towards my right side like this, and hydrogen was coming to the left side. In case of 5, 4, the 3 is coming to the left side and hydrogen is going towards the right hand side. Similarly, if you see the 5th carbon, the C6 will be coming towards the right side and this is going back. So it is not visualized here, but it is going backwards. See, in the similar manner is this one. So we combine again as we combined in the earlier ones, and we see that the 6 common, we combine the 2 butanes in the eclipse form. So it is a very easy way of drawing chair and boat conformations by drawing the if you are drawing the chair form, you draw 2 butanes in a gauche form, combine the 2 common methyls, and from the front and the back you have to combine the front wala with the front wala and the back wala with the back carbon methyls. And similarly in the eclipse form, if you do, you get the boat form. So you can say that boat is least stable because all carbon-carbon bonds are in the eclipse form. And there is one more interaction, which is the flagpole interaction, because hydrogens are coming towards one another and this distance is very less, and because of this interaction also there is an unstable condition generated, and boat conformation is the least stable out of the 3. The other thing needs to be mentioned here, the last point, is the substituted cyclohexane. So as you can see on the slide that I have placed the bonds, the cyclohexane, there are all the carbons are having 2 bonds. So there are 2 types of bonds, one which are going perpendicular to the chair. So they are standing like this, up or down. So alternately they are down, up, then 5th is down, then 6th is up, then 1 is down, then 2 is up. So these all hydrogens are called as axial hydrogens. So axial hydrogens, if I replace one of the hydrogens by methyl, then what is happening, I have painted in red all the axial positions. Then this methyl is in close proximity to the C2 methyl, is in close proximity to the hydrogen of C6, and if you draw the other structure, then the hydrogen of C1. So these generate what are called as 1,3 diaxial interactions. So the stability of 1-methyl cyclohexane would be greater, not in the case of axial but the other form, which is called as the equatorial form. Equatorial form is now the carbons are having the hydrogen bonds are going up and down, but not perpendicular to the plane but in the other direction. So these all bonds which I have marked here are equatorial bonds, and in this case when I draw the structure, this red comes on this one, and when it comes on this one, there is no flagpole type of situation like 1,3 diaxial interaction with the other carbon hydrogen bond, and this methyl is very much stable on the equatorial form. So this equatorial, so please do not take it like the case of axial and equatorial. I have placed 2 different structures, one showing only the axial forms and the other showing only the equatorial form. So when you draw a chair form, then you have to draw all the bonds which were present in both the structures. So all 6 carbon hydrogen bonds as axial perpendicular to the chair, and all equatorial 6 carbon hydrogen bonds which are going in the different direction. The axial bond, if it is up, then the equatorial bond goes down and vice versa. And when you flip the chair like we did earlier in the plot, then what happens is all the axial bonds are converted into equatorial forms. So I can say that in case of 1-methyl cyclohexane, when you would say that only equatorial cyclohexane should be present, but methyl with equatorial position should be present, but it is not the case. Both are present and they are interconvertible into one another, and out of the 2 structures, when methyl goes on equatorial form, then it is the more stable form. So you may go and read about the 1,2 disubstituted and 1,3 and 1,4 disubstituted molecules and have a look at their conformations. Thank you very much for your patience.
Dear friends, due to paucity of time, we have to stop our lecture here. On that note, we would like to thank Dr. Khanna for coming to our show and delivering this wonderful lecture. And thank you, dear friends, watching our show. Stay tuned and keep watching. Thank you.